Well, how does this differ? In Dijkstra's, we were looking at paths, and in Prim's, we only care about edges. So we actually do quite a bit less work with Prim's algorithm compared to Dijkstra's algorithm. All right, well, let's go through a proof of Prim's algorithm. So here's our theorem. Our claim is that Prim's algorithm always computes the or a minimum spanning tree. It turns out you can have multiple correct minimum spanning trees when you have tied edges. But like I said, we're going to ignore those cases. So we're going to say that it computes the minimum spanning tree when given a connected graph. So we need to prove two things: that Prim's actually creates a spanning tree, and that the spanning tree is the minimum spanning tree. And to do that, I'll need to define a few graph properties for you. The first is called a graph cut. And we're going to say that a cut of any graph is a partition of V into two non-empty sets. So here's a graph. A cut would be like this, where I put all of the vertices into two non-empty sets. So for example, all these vertices and all these vertices. So here's our AB cut. And we have some edges that cross the cut, and those would be called crossing edges. And a good place to start here to make sure that the graph cut makes sense is for a graph with n, is to start with this question: for a graph with n vertices, how many possible cuts can you create? Some of these answers are easier to eliminate than others. So for example, for this graph, I could single out this vertex, and that's one cut. I could single out this vertex, that's another cut, and so on. So I can pretty easily come up with n cuts, and that's just by singling out each vertex individually. But then I can also section them out by twos, and I can do that n over 2 times. So it should be pretty easy to, or more than n over 2 times actually, it should be pretty easy to eliminate the big O of n answer. Another answer that should be easy to eliminate is this n to the n one. N to the n is sort of greater than factorial, and it will almost never be sort of the correct answer. So based on intuition, I would just say eliminate that one. So we're really left with two reasonable choices here. And the easiest way to think about this is that essentially for each vertex, so take this one, I'm going to flip a coin and put it into A or B. I'm going to repeat that process for every vertex. So that means I have a binary choice for all n vertices. So that means the total number of cuts I can have is 2 to the n. Alright, so why are we talking about cuts? Well, if we go back to Prim's algorithm, we do have a cut each time through. We have all of our vertices that are in found, and all of our vertices that are not in found. So this is going to be a set subtraction. Alright, so a graph cut is one thing we should talk about. Another is empty cuts. So the empty cut lemma says that a graph is not connected if there exists a cut with 0 crossing edges. So here's the A set, here's the B set or partition, and there are no edges that go across that cut. Well, there are two different ways you can prove that the cut lemma is correct, so this being the cut lemma. So let's assume that we have 0 crossing edges. We can pick any u in A and any v in B, and there will be no path from u to A. Thus, the graph is not connected. So if there's no path from u to v, that means they're not connected. We could do this in the opposite way. We could say, let's assume that the graph is not connected. And let's assume that there's no path from u to v. Well, what we can do is we can put all of the vertices reachable from u into one partition and all the other vertices in B, and there are no edges that cross the cut. So that's two different ways to say that if the graph is not connected, there exists a cut with 0 crossing edges. Another lemma that will be helpful here is the double crossings lemma. So the double crossing lemma says that suppose the cycle C has an edge crossing the cut AB, then there must be at least one more edge in this cycle that crosses the cut. So for example, if I have this cycle between these 3 vertices, and I have one crossing edge, I have to have another crossing edge, at least one more crossing edge. So if I go over here, I've got to have some other way to get back, assuming I'm on a cycle. Well, there are a number of different ways you can do that. So for example, here's a cycle. I could also have multiple crossing edges through the cycle. So here's a cycle where I go zigzag back and forth. And all this is telling us is that there's guaranteed to be at least one more edge in a cycle that crosses the cut. A corollary to this is that if E is the only edge crossing some cut, then it cannot belong to any cycle. All right, so all these graph properties are going to help us do our proof of prims.